All right, so today we're going to talk about chapter 5, which are z-scores, which are location of scores and standardized distribution. So we're just taking things a little bit higher, a little bit more complex when it comes to statistics each week. First off, we need to identify and describe the location of every score in a distribution. This will help us standardize the distribution. We can take different distributions and make them equivalent and comparable and comparable to each other. Z-scores are called standard scores, and they help us do that. If we look here at figure 5.2, it shows us the distribution of exam scores. For each distribution, the mean is 20, but for one distribution, we've got 2, and the other we've got 10 representing S, and the relative position of your score is X equals 26. This is very different for both of those two distributions. Exact location of a score within a distribution is described by a z-score. We use the plus or minus sign to tell us whether the score is located above in a positive position or below in a negative position of the mean. The number tells the distance between the score and the mean in terms of the number of standard deviations. So in figure 5.3, we've got the relationship between z-score values and location values. The z-score formula for a population is indicated on the screen. The numerator is a deviation score, and the denominator expresses the deviation in standard deviation units. Here's how we can determine a raw score from a z-score. We're going to have to algebraically solve for x and reveal that information. And then we have to take a raw score, which is simply the population mean, plus z multiplied by the population standard deviation. So the easiest way and the most common way for us to compute a z-score are going to be using populations. It is popular to calculate a z-score from a sample, but it's not as common. It will help us indicate relative position of the scores in a sample and the distance from the sample mean. A sample distribution can be transformed as well into z-scores. That will help with the same shape as the original distribution and the same mean and standard deviation. Let's go ahead and have our first learning check for chapter 5, which says a z-score of z plus 1 indicates a position in a distribution that's A, above the mean by 1 point, B, above the mean by a distance equal to 1 standard deviation, C, below the mean by 1 point, or D, below the mean by a distance that's equal to 1 standard deviation. And that correct answer is going to be B, because that's what a z-score does. It tells us the distance that's equal to the standard deviation, how much something falls above or below the mean. Here's our second learning check. True, false. A negative z-score always indicates a location below the mean. And the second one, a score close to the mean, has a z-score close to 1. Give you a few moments to think about the correct answer. And the first one is true. The sign indicates the score is below the mean if it's negative. But then our second one is actually false. Because if a score is close to the mean, then it's going to be 0 instead of 1. If it was at 1, it would be above the mean. There are a few other relationships that exist between z-scores and the mean and standard deviation. So a z-score is going to help establish a relationship between the raw score, the mean score, and the standard deviation. When we're given a mean, a raw score, and a z-score, you can compute the standard deviation. When you're given the standard deviation, a raw score, and a z-score, you can also compute the mean. Here's another figure for us to look at. If we look at figure 5.4, it gives us an example, a visual representation of the question in example 5.5. If 2 standard deviations correspond to a 6-point distance, then 1 standard deviation must equal 3 points. And if we look at this one, this shows us that if there's a 12-point distance from 42 to 54, which corresponds to 3 standard deviations, the standard deviation would then have to be 4. And then our X number would be 42. And that would be below the mean by 1 standard deviation. So the mean would be about 46. For our second learning check, for a population with 50 and 10, what is the X value that corresponds to Z equals 0.4? Is it A, 50.4, B, 10, C, 54, or D, 10.4? Give you a few moments to think of your response. And then our correct answer is going to be C, once we calculate that out. For our second learning check, if 40 and 50 correspond to Z equaling plus 2 and 10 points, is that true or false? And then if we've got sigma equaling 20, and that's a score above the mean by 10 points, will we have a z-score of 1? We've got false and false. And I hope that makes sense, because it would actually be 0.5 and 5. When we use z-scores to standardize a distribution, every x value can be transformed to a z-score. And that z-score transformation is exactly the same shape as the original distribution of scores. Having a mean of z-score distribution is always 0, and the standard deviation is always 1. That z-score distribution is going to be called a standardized distribution. If we look at figure 5.6, we can see that we've got an entire population of scores that's been transformed into z-scores. That transformation does not change the shape of the distribution, but the mean is transformed into a value of 0, and the standard deviation is transformed to a value of 1. When we look at the x-axis and how we can relabel it after there's been a z-score transformation, we can see in this example that relabeling has happened, and the distance that is equivalent to 1 standard deviation on the x-axis, which is 10 points in this example, is going to correspond to 1 point on the z-scale score. So when we use z-scores for making comparisons, they're going to be comparable to each other, and they're going to be different distributions, which can be converted to z-scores. We also have standardized scores, which allow for the direct comparison of scores from two different distributions because they have been converted to those same scales. When we have the process of standard deviation being used very widely, we can have some different formulas used. For the SAT, there's usually an average of 500 with the variance of 100 points. And then for IQ, we can have the average IQ being 100 points with a standard deviation variation of 15 points. When we have a standardizing of a distribution, we are going to use two steps. We're going to take those original scores, they're transformed into z-scores, and those z-scores are transformed into new x values so that those specific means and standard deviations can be obtained. If we look at figure 5.6, we can see that the distribution of exam scores from the example in example 5.10, the original distribution was standardized to produce a distribution with a mean of 50 and a standard deviation of 10. And each individual is indicated by an original score, a z-score, and a new standardized score. For example, Joe has an original score of 43, a z-score of -1, and a standard deviation of 40. So for our third learning check, if we've got x equaling 59, which comes from a distribution with a mean of 63 and a standard deviation of 8, this distribution is standardized to a new distribution with a mean of 50 and a standard deviation of 10. What is going to be the new value of that original score? 59, 45, 46, or 55? Few moments to think about your answer choice. And that correct choice would be 45. So inferential statistics are going to be techniques that use the information from samples to answer questions about populations. It can also help us interpret research results that depend on whether the sample is noticeably different from the population. One technique for dividing noticeably different is using z-scores. As we look at figure 5.10, we see a diagram of a research study. The goal of the study is to evaluate the effect of a treatment. A sample is selected from the population, and the treatment is administered to the sample. If after treatment, the individuals in the sample are noticeably different from individuals in the original population, then we have evidence that our treatment has had an effect. And then figure 5.11 shows us the distribution of weights for the population of adult rats. The individuals with z-scores near 0 are typical or representative of the population. However, individuals with z-scores beyond +2 or -2 are going to be considered extreme and noticeably different from most of the others in the distribution because those scores are outliers. They're too far away from the mean. So for learning check 4, last week Andy had exams in chemistry and Spanish. On the chemistry exam, the mean was 30 with a standard deviation of 5, and Andy had a score of 45. On the Spanish exam, the mean was 60 with a standard deviation of 6, and Andy had a score of 65. For which class should Andy expect the better grades? Chemistry, Spanish, or there's not enough information? So I'm going to give you guys a few moments to think about which of these answers might be most correct. And the correct answer is going to be chemistry, because his chemistry score was much higher than the mean, and there was more variance there. And for our learning check 4, true false, when we transform an entire distribution of scores into z-scores, we will not change the shape of the distribution. And the second question, if we have a sample of 10 scores that are transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. Take a few moments to think about the correct answer choices. And for our first choice, it's going to be true. When we have the location of a score which is relative to all the other scores, it's going to be unchanged. So the shape of the distribution will not change. So that is indeed true. For the second question, the number of z-scores which are above or below the mean will be exactly the same as the number of original scores that are above or below the mean. So that wouldn't change. So that is everything that I had to tell you guys about z-scores, and I hope that has helped in your understanding of them.